Hello, ladies and gentlemen. We're going to do 9.7a today. We're going to start our work with the Taylor and Maclaurin polynomials. Our objectives are that we're going to find approximations of elementary functions and compare them with elementary functions. I know that seems really weird, but I'll explain in a moment. And then we're going to find Taylor and Maclaurin polynomial approximations of elementary functions. Alrighty, so here's kind of the basic idea. So let's say I have a function, and it looks kind of something like that. Well, and we've done this process kind of before. We'll talk about that. I can find another function at the same point that's going to very closely approximate the original function. So we would say that I have a polynomial, or I'm trying to find a polynomial centered at C, and then I want to find another function that's going to help me approximate. So I'm looking for another function to approximate the original function. Okay, so I'm going to say that P of C is going to equal F of C. So this is a polynomial that we're looking for, and I'm going to use it to approximate the original function. Well, and if that's true, then this is also true, so F prime of C. So then I'm going to add a statement that says that the derivative is going to be the same as the derivative of the original function, and the two functions are going to have the same slope at that particular point. Okay, so we are looking for a polynomial function where the polynomial evaluated at C is equal to the function evaluated at C, and at C, both the original function and the polynomial approximation have the same slope. Okay, so let's just do an example. And we have a little bit of long notes today, so I'm sorry about that, but I'm going to try to condense it a little bit as we go. So the first example says, find a first degree polynomial, and I'm just going to write poly. Find a first degree polynomial for the function, and our function is going to be f of x is equal to e to the x, okay, whose value and slope, which is just what we talked about here, agree with the value and slope of the original function at x is equal to 0. Alrighty, so as we move through the first example, we're kind of setting up how the Taylor and the Maclaurin polynomials have been developed. Alrighty, so I'm looking for a first, that's what the 1 means, first degree polynomial, and so it's going to be an initial value plus the next value times x. Okay, so this would be a first degree polynomial. Notice that this would be my initial value or my y-intercept. Okay, and then I'm going to have a slope times x. So then I'm going to write f of x is equal to e to the x, and f prime of x is e to the x, because we love e to the x because it's super simple. Okay, so then I'm going to do f of 0, and I'm going to get e to the 0, which is 1, and I'm going to do f prime at 0, because that was where they wanted me to find a polynomial to approximate. E to the 0 is also equal to 1. So then, if you notice, now I can start substituting in my values. Okay, so my polynomial at 0 is going to equal f of 0. So then I'm going to have a sub 0 plus a1 of 0 is going to equal 1. Okay, and then if I look at this, a1 of 0, this is 0. So I get a sub 0 is equal to 1. Okay, well then I can do p prime of x is equal to a sub 1, and then I know that P prime, oops, that's supposed to be a P, of X is going to equal F prime of X, and then I know that A sub 1 is equal to 1. So the polynomial that I was looking for is going to be 1 plus X. And I think that example is a wee bit confusing, and I think it gets simpler as we move along. Alrighty, so one of the things that you need to notice is that we used a linear function to approximate another function. And we've done this before, so if you'll remember, when we did Newton's method a million years ago, Newton's method did the same basic thing where I used a linear function, a first degree function, to actually find or approximate another function, okay? So the other thing to notice, and I'm going to go back to this little example that I had, is my linear example is really good right at that specific point. But if I chose other points, and as I move further away, then my linear approximation is not as accurate. So then we're going to add additional criteria, and we're going to start adding the second derivative, the third derivative, etc., and we're going to generate higher degree polynomials. Okay, so what that means then is, let's say I have P2 of 0, and this would be a second degree polynomial, okay? And so then if I have this situation, I'm going to know that this is going to equal f of 0. So I want a second degree polynomial to approximate the original function. So I'm going to know that p prime of the second degree, 0, is also going to equal the slope of the original function. Well, then I'm going to add additional criteria. So I'm going to say the second derivative at that point is equal to the second derivative of the original function. And I could keep going on and on and on, okay? So then I would say that P2 of x is equal to 1 plus x, because that was the original, plus 1 over 2 factorial times x squared. And I could keep adding higher degrees of polynomials, and then it would make it be even more an accurate, boy, that was bad grammar, sorry, that would make it be a more accurate representation of the original function. Okay, so that means that we're going to develop kind of a general rule, and then we're going to develop another general rule in just a minute. But if I want a polynomial of any degree to represent a function, it's going to be 1 for this, and we're still working with our e to the x, by the way. So x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed plus etc., 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 1 over n factorial times x to the n. All right, so this would be an nth degree approximation. Alrighty, so when we did this particular example, we were looking for a c value that's in the domain of our original function. It does not have to be 0. In this particular case it was, but it could be anything. So I'm going to write could be anything. Well, because you have to think about almost like a translation, that's going to help us develop our overall general rules. So I'm going to give you kind of a formula. So this is going to be an nth Taylor polynomial. I know it seems a little bit nebulous at this point, but I think as we walk through some examples, it will start to make more sense. And we're going to have an nth Maclaurin polynomial. Alrighty, so this is kind of important. This is going to be our general formula. It says if a function has n derivatives, okay, at a given point C, then the polynomial Pn of x is equal to f of c plus f prime of c times x minus c plus f double prime of c and x minus c squared over 2 factorial plus, then I'll do another one, f triple prime of c times x minus c to the third over 3 factorial, okay? And I think the lighting's a little bit weird today, so sorry. Maybe I can make it be oh, look at that. Let there be light. And then this would go on and on and on until I had the nth derivative evaluated at c, x minus c to the n over n factorial, okay? So this is going to be the Taylor polynomial. And for the Taylor polynomial, my c does not have to be 0. My c can be anything. And then as a matter of fact, if c is equal to 0, then we call that a special Taylor polynomial. Polynomial, that's a hard word to spell. And that's going to be the Maclaurin polynomial, okay? Gosh, I can't spell that word. So, if I am trying to find a polynomial approximation at a given value of c, and c is not 0, then that's a Taylor polynomial. If c is equal to 0, then that is a Maclaurin polynomial. Alrighty? So, if this is true, then that means that I'm going to have f of 0 plus f prime of 0 times x plus f double prime of 0, x squared over 2 factorial, because when I subtract x minus c, and if it's 0, then things go away. That's pretty nice. And then I would have the third derivative evaluated at 0, x to the third over 3 factorial. And then I would keep going dot, dot, dot until I have f to the n evaluated at 0, x to the n over 4 factorial. Alrighty, so now let's start doing some examples. So one of the things that I would tell you is as my degree increases, the accuracy of the polynomial approximation also increases. Alrighty? Okay, so let's do an example. And actually, I guess it's not going to be so horribly long. I want to find the Maclaurin polynomial for, I forgot a word. Find the nth Maclaurin polynomial for f of x is equal to e to the x. Okay? So that means that I'm looking for Pn of x, which is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime 0 x cubed over 3 factorial plus dot, dot, dot. It's going to be f to the n evaluated at 0, x to the n over n factorial. So one of the ways that I like to do these is I like to just start organizing my math. So I'm going to write here that I have f of x is equal to e to the x, and f of 0 is e to the 0, which is 1. Okay? Then I'm going to take the derivative, which is really nice with this function. I still get e to the x, and then the derivative evaluated at 0 is still 1. And then the second derivative, I mean, this is just not very exciting, f double prime of 0 is 1, etc., etc., etc. Okay? So then if I write the nth Maclaurin polynomial, so Pn of x is going to equal the function evaluated at 0, which was 1, plus the derivative evaluated at 0, which is 1 times x, plus the second derivative evaluated at 0, 1x squared over 2 factorial, and then I could have kept going. So the third derivative, because they're all the same, evaluated at 0 would have been 1x cubed over 3 factorial plus dot, dot, dot. So it's going to be 1x to the n over n factorial. Okay, so that would be the Maclaurin polynomial for f of x is equal to e to the x. Alrighty, so let's do another example. So it says find the Taylor polynomials, and I have P0, P1, P2, that's a P3, P4, for f of x is the natural log of x centered at c is equal to 1. Okay, so 1 is in the domain of the natural log of x, and so that means that I can manage my math. All right, so we're going to do the same basic process that we did here, and then we'll use our generic formula. So my function f of x is the natural log of x, and the natural log of x evaluated at 1, natural log of 1 is 0. Okay? And then I have the first derivative is going to be 1 over x, and then the derivative evaluated at 1 is 1 over 1, which is 1. Okay? My second derivative, this is x to the negative 1, is going to be a negative x to the negative 2, which is a negative 1 over x squared. Then the second derivative evaluated at 1 is a negative 1. Okay? The third derivative, 1, 2, 3 of x, is going to be a positive 2 x to the negative 3, which is 2 over x cubed. Scoot my paper up a little bit. Okay? And then if I evaluate the third derivative at 1, I get 2 over 1, which is 2. Alrighty? And then the last one that they wanted me to do is the fourth derivative of x is going to be a negative 6x to the negative 4, which is a negative 6 over x to the fourth. And then the fourth derivative evaluated at 1 is a negative 6. Alrighty. Oops. Okay, that's correct. So one of the things that they want you to notice is that a negative 6 is a negative 3 factorial. Okay? So now let's start substituting all of our numbers into our Taylor polynomial. Okay? And I'm going to do this kind of one step at a time, and then the next time we can skip doing it in quite such a tedious manner. Alrighty, so we know that the Taylor polynomial for x is going to be f of 1, and so this is going to be 0. Okay? Alright, I can't show you both pieces of paper, so you're going to have to refer back. Ooh, maybe I can do it over here. I'll come up and put a squiggly line because it'd be nice if we could still see that information. So the first degree polynomial would be f of 1 and then plus f prime of 1 times x minus 1. Okay? And so this was 0. And f prime of 1 is a negative 1. So then this is going to be oops, that's double prime. F prime of 1 is 1. So this guy is 1. So this is going to equal x minus 1. So then the second degree polynomial is going to be the first guy plus the second guy plus the third guy, and that's going to be f double prime at 1 over 2 factorial times x minus 1 to the second. So remember, this guy is 0, this guy is 1, so this is going to equal x minus 1 plus, and then I have f double prime was a negative 1 over 2 factorial times x minus 1 to the second. Okay? All right, let's see if I can squeeze both of these in here. P to the 3. P to the 3, if we just start kind of taking some shortcuts, is going to be p to the second plus the next one. So I'm going to write p2 of x, and then I'm going to write p3 of x, which is the third derivative of x times x minus 1 to the third over 3 factorial. Well, p2 of x was going to be x minus 1 over 2 factorial, x minus 1 to the second. Whew, now I have to write this stuff. The third derivative, evaluated at 1, was 2, times x minus 1 to the third over 3 factorial. And then I have one more to do. Okay, so I'm going to try to squish it in. So the fourth degree polynomial is the third degree polynomial plus the fourth derivative evaluated at 1 times x minus 1 to the fourth over 4 factorial. And I can't get it all in, so I'm going to go to another page. Okay, so if I fill in my fourth degree, so I'm going to have my third degree, so p4 of x, okay, except you can't see it, there it is. So now I'm going to have the third one, which was x minus 1 over 2 factorial, x minus 1 squared, 2 over 3 factorial, x minus 1 to the third. And then the fourth derivative evaluated at 1 was a negative 6. There's 4 factorial, x minus 1 to the fourth. Whew! So that is your fourth degree polynomial. And this one would be a Taylor polynomial because c wasn't 0. Alrighty. I think I have one more example and then we're done. So it's not as bad as I thought. Alrighty. So this one's going to say, find the Maclaurin. And remember, for the Maclaurin, that means that my c is going to equal 0. Find the Maclaurin polynomial, p sub 0, p sub 2, p sub 4, p sub 6, for f of x is equal to the cosine of x. And then I want to use the sixth degree polynomial to approximate the value of the cosine of 0.1. Alrighty, so I'm going to find this value in my calculator, and then I will compare it with what we find for the sixth degree polynomial approximation. Alrighty, so when I first looked at this example, I thought this situation was fairly unique. And so I didn't quite understand why they were only asking for the evens, but I'm going to show you all of them, and then you'll understand why. Alrighty, so my original function, f of x, is going to equal the cosine of x, and f of 0, the cosine of 0 is 1. If I take my first derivative, I'm going to get a negative sine of x. And if I evaluate the first derivative at 0, the sine of 0 is 0, so this guy is 0. So if you'll notice, since the derivative is 0, when I substitute that into my polynomial, I'm going to end up with a 0 term, which is why they don't include the first. Okay? My second derivative is going to be a negative cosine of x. Then my second derivative evaluated at 0 is going to be a negative 1. My third derivative is going to be the sine of x, and the third derivative evaluated at 0 is 0. So notice again, I didn't have the third derivative in there because the odd derivatives are going to be 0. And then my fourth derivative is going to be cosine of x, and then my fourth derivative evaluated at 0 is 1. So notice that our pattern, we have developed a pattern, so it goes 1, 0, negative 1, 0, and then it would start all over again, okay? So now I'm going to start filling in our information. So P0 of x is going to be f of 0, which is 1. The first degree polynomial is p sub 0 plus f prime of 0 times x. Well, this was 0, so that went away, and this was 1, so my first degree polynomial is just 1. Okay? So then my second degree polynomial is the first degree, so p1 of x plus, and I'm doing it this way because it's a little bit easier on the notation, okay? So then it's going to be plus my f double prime of 0 times x squared over 2 factorial. Okay, well, p1 of x was 1, so this is 1 plus f double prime is a negative 1, so negative 1x squared over 2 factorial. Okay, then I'm going to go to the third degree polynomial. So it's going to be the second degree plus f triple prime of 0 x cubed over 3 factorial. But if we look at the third derivative evaluated at 0, I get a 0, so that means that this is going to go away. So that whole expression goes to 0. Okay, so it's still just going to be this. So then my fourth derivative is going to be, turn the page so I don't screw something up, the previous derivative, so p3 of x plus the fourth derivative evaluated at 0, x to the fourth over 4 factorial. So this is 1 minus x squared over 2 factorial, because that was p2, and then it was p3, and then plus the fourth derivative is 1, so x to the fourth over 4 factorial. And then my sixth, the pattern's going to continue, so the fifth is going to go away. So I went negative, positive, so the next is going to be negative x to the sixth over 6 factorial. Oops, sorry, I shouldn't put that there, that's bad. So p to the 5 is going to be like p to the 3. There's not going to be a value, so it's going to be the previous. So the p to the 6th of x is going to be p to the 4th, and then plus the sixth derivative, which is going to be, so this is 4, this would be 5, this would be 6. So then it's going to be the sixth derivative evaluated at 0, x to the 6th over 6 factorial. This guy's going to be a negative 1, which is what I've done there and I scribbled out. So this is 1 minus x squared over 2 factorial, x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, okay? And this would be my sixth degree polynomial approximation. So now that I can stay on the same page, I'm going to use this to approximate the cosine of 0.1. So now I'm going to do that up here. Let's do it in another color. So if I evaluate p of 6 at 0.1, I would get 1 minus 0.1 squared over 2 factorial plus 0.1 to the 4th over 4 factorial minus 0.1 to the 6th over 6 factorial. And if you do this math in your handy-dandy grapher, you would get, and I'm going to write down all of the decimal places, 9950416.5. And if you run this through your calculator, so if you do the cosine of 0.1, remember it would have to be in radians, you would get this exact value. So the sixth degree polynomial is very close to the actual value when you do this in your calculator. Alrighty? One last little closing note to notice is that for the cosine of x, the Maclaurin series has only even powers of x. Oops. Okay, and I don't know that you need to memorize that, but if you happen to remember it, it would just save you some work. And then the sine of x, Maclaurin series. And remember, this means that c is equal to 0. Series has only odd powers of x. Okay, so if you remembered that, that would be great. If you don't, the world won't come to an end. Alrighty, that's it for today. I will see you tomorrow.